All right. Thanks a lot for that introduction. Right. I think it was 2005, and probably you should blame your former colleague, Johan, who left, also in 2005.
He also didn't like me.
I guess students do take after their advisors. OK, great. Right. So thanks a lot for showing up on a Friday evening on a lovely day. In the final talk, I want to discuss some connections between prismatic homology and algebraic topology. I hinted at this on the first day, and I would like to sort of go into a little more depth today. But maybe before I start, I just wanted to advertise something, which is if you're interested in the kind of stuff I've been talking about, there will be a special year at the IAS in 23-24 on this topic. So I encourage you to check it out. OK, so what's the goal? Let me start over here. So the goal is to explain an algebra geometric analog of a certain classical result in algebraic topology. More precisely, it concerns K-theory. And so let me just recall a reformulation of the combination of Atiyah-Hirzberg's spectral sequence and Bhatt periodicity. So it concerns the topological K-theory of a nice topological space X, and here's one way to state it. So for a reasonable, which I won't go into, space X, there exists a natural filtration on its topological K-theory whose graded pieces are computable. So there exists a filtration on complex K-theory of X, which is a spectrum. So it has homotopy groups with graded pieces described as follows. So they're just given by cohomology of X with appropriate shifts. And since I want to do everything in some derived sense, let me write down the cochain complex over here rather than its homology. And so secretly, what the result is really saying is that there is a spectral sequence that computes the K-theory of X from its cohomology. You have to keep track of indices. And sort of what powers this is Bhatt periodicity, which essentially proves this theorem when X is contractible. So when X is contractible, this just says that the complex K-theory of a point is going to be a bunch of copies of Z placed in even degrees, which is what that gives you. And so what I would like to do in this talk is explain a variant of this in algebraic geometry. So the goal, or more precisely, a variant in algebraic K-theory. So describe a variant for algebraic K-theory. So algebraic K-theory was an analog of topological K-theory that was eventually written down by Quillen. And it's notoriously hard to compute, but it's also notoriously important. I mean, it shows up in a lot of different parts of math in various conjectures and calculations. Correct. So the question was whether the filtration splits in characteristic 0 using the Chern character, and the answer is yes. So when formulated like this goal actually goes back to some foundational conjectures of Beilinson in the 1980s. He had this kind of vision of a theory of motives, and it was powered by some version of this conjecture. That conjecture has been solved essentially by the construction of the theory of motivic cohomology. And what happens there is that there is a filtration on algebraic K-theory where the graded pieces are given by motivic cohomology rather than singular cohomology. This is great. But one sort of problem is motivic homology is really hard to compute. I mean, motivic homology is basically Chow groups. So if you try to compute it, you run into very difficult questions about algebraic cycles. And so what I want to describe today is a variant where you're not so ambitious. You don't try to compute algebraic K-theory. You try to compute some like softening of it, where you have much more control on what the graded pieces are going to look like. And so let me just state that more precisely. So more precisely, we want to compute. You want analog for what's called Italki theory. And I'm going to p-adically complete everything. I remind you, p was implicitly fixed on lecture 1. And so Italki theory, I mean, formally speaking, the way it's defined is that you think about algebraic K-theory as a functor on rings or schemes or whatever, and then you sheafify it for the Ital topology. The advantage of doing this is that once you have something which has Ital descent, there's a good chance that you might be able to compute it, because we have a lot of tools to compute things related to Ital homology. And so, OK, if you don't know what these objects are, just pretend that this is some kind of a slightly modified version of K-theory. And I should also say that this question has been solved if the input algebra is sort of as far away from P as possible. So if P is invertible on the input algebra, this is the subject of classical results of Suslin and Gaber and Thomason, and probably other people I'm forgetting. And so the sort of main remaining case is what happens if you plug in something which is p-adically complete, and the output is also p-adically complete. So analog of blah on p-complete rings, p-adically complete rings. For example, the ring could be a mod p, like an FP algebra. OK. So I would like to address this question today. So prove an analog of this result for this object. Any questions so far? Yes, absolutely. So this is a good point. Everything in my life is commutative. So I'm definitely restricting to the commutative case. Now there's this marvelous result of Dustin Clausen and Akhil Matthew that says that K-Ital essentially can be described as a non-commutative invariant. There's this thing called Selmer K-theory, and they're more or less the same. So the invariant does make sense for non-commutative rings. But I don't know an analog of the result in that setting.
So is Marita invariant?
Selmer K-theory is, right. OK, so that's the question. And the answer, perhaps unsurprisingly, given the topic of this lecture series, is going to be that the relation between topological K-theory and singular homology is going to be similar to the relation between Ital K-theory and prismatic homology. Except it's not quite prismatic homology. You have to modify it a little, somewhat. And the modification is actually interesting. So let me spend a little bit of time on this. So this is called Syntomic Homology. This is an invariant that was, at least in some avatar, has been studied a lot in arithmetic geometry. And I'll try to give you just some kind of a bare bones definition of it in terms of the kind of structures one sees on prismatic homology. I will not give a precise definition of prismatic homology, but I'll at least tell you what it looks like. So let's say R is a p-adically complete ring, commutative. So this theory of prismatic homology, what does it do? It produces for you a bunch of objects attached to R. So the first player is the prismatic homology of R itself. And so this is a commutative algebra object in the derived category. If you like, it's an E-infinity ring spectrum. It's even has more structure than that. So to a first approximation, it's a complex of abelian groups with some kind of an algebra structure. You get a certain line bundle over this ring. So an invertible module over this ring. So this is called the Breuil-Kissen twist, because some version of it was defined in the work of Breuil and Kissen in Gala representations. That will become relevant in a moment. The most important piece of structure is the Nygot filtration. So, well, sorry, those are Frobenius as well, which I forgot. Sorry, that's probably the more important piece of structure. So there's an endomorphism phi, which is called the Frobenius. And you're supposed to think of it as saying that phi is a lift of the Frobenius on the ring mod p. So if you reduce this object mod p, you get some kind of a commutative ring in Kiersig p. So you imagine it has a Frobenius endomorphism, meaning x goes to x to the p. And this phi is a lift of that. So it's an endomorphism that's defined without going modulo p. So the question was, what kind of a homomorphism is it? So I mean, for the purpose of my talk, it's a homomorphism of the infinity ring, so it's only in some weak sense. But in any kind of standard model you would use to compute this, you would get like an actual cosimplicial ring and an actual term-wise endomorphism of that cosimplicial ring. Yeah. So the filtration, which is called the Nygot filtration, it's rather useful. It plays the role of the Hodge filtration in the story. So if you're familiar with the Hodge filtration from complex geometry, this seems to be some kind of a p-adic analog of that. And these structures are supposed to interact in a certain way. And the way they interact, roughly, is that this Frobenius, if you restrict it to fill I, it has a certain divisibility property. So you can divide it by a certain element, except you can't really talk about elements, and that's what this twist is doing. And so what you get is a divided Frobenius endomorphism, which goes from fill I, Nygot, prism R twisted by I, to prism R twisted by I. So the twist by I is the twist by the I-fold power of this invertible module. And the twist is necessary in order to obtain such a map, which is phi semilinear. So let me call this phi r. So this is phi r semilinear. OK, I apologize. There's a bunch of objects. But now you sort of, if you believe such a structure exists, you immediately observe that, well, there's actually two maps from here to here. There's this phi I map that I told you about. There's also the obvious map. I mean, fill I is some kind of a filtration on prism R, and so I can just twist it by I. I get a new filtration. I get a new map. And so you can contemplate at least the difference between those two operators. And that's the definition. So the ith Syntomic homology of a ring R is defined to be the equalizer of those two maps. Or equivalently, it's the fiber of the difference. And so this is going to be the analog of this object for Gur I eventually. OK, so the precise details don't really matter. The takeaway is there's some cohomology theory called Syntomic homology that you concoct by thinking about prismatic homology and the Nygot filtration on it. And there's a recipe to compute it in terms of these two objects and these maps. Is that OK? So this I mean, I guess this name was coined by Maser for, oh, OK, let me not explain the reasoning. Let me make some easy remarks on this first. So first of all, you might wonder if you need all this fancy machinery to define this object, given that I told you it was defined earlier. And so if, this definition seems to be the right definition with integral coefficients. If you don't care about torsion, so if you allow yourself to invert P, then this was essentially constructed earlier. by Fontaine and Messing in their early work on p-adic Hodge theory. And this was kind of one of the first approaches to proving the analog of the de Rham comparison in p-adic Hodge theory. The question was, did they make any assumptions on R? I mean, surely they did, because they were using crystalline homology, so there was some finiteness assumption. Probably it was assumed to be syntomic. But yeah. The definition had a similar flavor, except instead of prismatic homology, you use crystalline homology. Great. Actually, yeah, sorry, there was just one remark on this. Let's see if that works. OK, so this is some invariant, and let me at least give you some examples of what it looks like, because I haven't really told you what the previous objects look like. So first example is what happens when you, maybe the first thing I should have said is that this only makes sense for I non-negative, yeah? So this is for I bigger than or equal to 0. And if I is less than 0, then I just declare the invariant to be 0, which is going to be a slight difference from what happens in topology. OK, so let me just tell you what the invariant is for weight 0. So ZP of 0 evaluated on R, well, it actually does nothing. So it's just supposed to be ZP, except you have to sheafify it for the Italki topology. And so the formal way to say it is the Italki homology of spec R, or spec R, with ZP coefficients. But you should think of it as saying that this is like the constant sheaf. It already starts becoming very interesting in weight 1, so ZP of 1, and I'll come back to that in a bit. For now, let me just tell you an example of the full invariant when R is very special. So take R to be a perfect field of Kersig P. It could just be a finite field. It could just be FP, in fact, but if you want to keep track of the Frobenius, it's slightly better to call it K. So then you might wonder, what are these objects? And they're super concrete. So prism R is the ring of Witt vectors of K. Phi R is the Witt vector Frobenius. So the usual, it's W applied to the Frobenius on R, or K. So if K was FP, then the Witt vectors of K is ZP, and the Frobenius is the identity map. The Nygot filtration is the p-adic filtration. So fill I is p to the I. And then this divided Frobenius map over here is what the name suggests. So and maybe I should have said the twist is trivial in this case. In fact, it's canonically trivial. So there's no harm in just ignoring it. And then the divided Frobenius map, it's supposed to be a map from fill I. I'm ignoring the twist. So it's a map from fill I back to the ring. So it's map from p to the I times w of k. P to the I w of k to w of k. And it's what you would expect from something which is called the divided Frobenius. So p to the I times x is supposed to be, you do the Frobenius and then divide by p to the I, which just means it's phi of x. In particular, it's an isomorphism, because k is perfect. And so that's one example of what this looks like. And in general, if your ring has a lot of p-power roots in it, like a perfect field, or also like a perfect ring, or a quotient of a perfect ring by a nice ideal, these invariants will live in degree 0. And so you'll be able to actually write down formulas for what they look like. They're not going to be complexes. They'll just be actual abelian groups. And so, OK, if you can try to compute what the Syntomic homology of finite field looks like, now that I've told you what all those objects are, if you don't want to follow the rest of the talk. But that was my very vague attempt at introducing Syntomic homology to you. And again, the takeaway is just it's some invariant defined in terms of prismatic homology and related to it by this fiber sequence. Any questions so far? So I want to go back to K-theory now. Back to K-theory. And so how is this object going to be giving us an answer to this, well, going to be realizing this goal? Well, I can formulate the theorem now. So this is a combination of the work of a lot of people. Probably the two most recent, okay, I guess I shouldn't have been Clausen, Matthew, Morrow, and myself, Morrow, and Schulze. But it builds on a ton of previous work in the area, and it's going to be exactly the same statement as over there. So there exists a natural filtration. We call it the motivic filtration. On Italki theory, I guess I didn't say what R is. This is a p-complete ring. Commutative. With graded pieces given by Syntomic homology. And shifted by 2i, just like in the Theorems. So basically what the theorem is saying is that the picture looks like in topology if you allow yourself to think of Syntomic homology in weight I as the analog of singular homology shifted by 2i. And this twist becomes actually more natural if you remember the way Bhatt periodicity works is that in pi 2i of complex K-theory of a point, what you see is not really z, but it's, well, it is z, but more canonically it's like z times 2 pi I to some power. And the power depends on which homotopy group you're looking at. So these twists are sort of p-adic analogs of 2 pi I. Okay. So let me mention one consequence of this theorem, which is a result back in algebra, even though the proof goes through this topological stuff. And it's a description of Syntomic homology in weight 1, so for ZP of 1. And I will mention why this is useful in a moment. So one good thing about K-theory is that, well, there are natural ways to produce elements in K-theory starting with things like vector bundles on your space. In particular, line bundles on your space give you elements of K-theory. And it turns out that ZP of 1 is exactly sort of trying to pick out the contribution of line bundles in K-theory. And so here's a more precise statement. So understanding this GER1 explicitly via the natural map from pick R, the line bundles on R, to K-theory of R leads to the following theorem. So maybe corollary is if I look at ZP of 1, which is GER1 evaluated on R, then this is essentially just pick. More precisely, it's the same kind of caveat that showed up in part 1 over there. There's some étale sheafification involved. And so the correct way to write it is it's R gamma, étale, sp of R with coefficients in GM. The cohomology of GM is the thing that computes pick. And everything is p-adically complete. And you have to shift by 1 because the relation between pick and GM involves a shift. But OK, so modulo decorations, ZP of 1 is a recipe for computing the Picard group of R. That's what this is saying. And so, OK, I will come back to this in a moment, but let me just maybe just point it out right now, which is this is something you could have just defined in algebra from the start, and it's something one often cares about. It's essentially the Picard group, or the Brouwer group, if you think about the one higher degree. And what this theorem is saying is that there's a way to compute these invariants in algebra in terms of things coming from prismatic homology, which tend to be more computable. And so we'll see some examples of that in a moment. But maybe the other remark I wanted to make before I tell you about that application is how sort of what the attributions are doing. So Clausen, Matthew, and Morrow proved a very general result, saying that Italki theory is the same as something called topological cyclic homology. Yep.
So in Picard group, operation of a line balance is standard group.
Mm-hmm.
And in K theory, vector bundles operation is direct sum.
Mm-hmm.
So how come you get a group homomorphism? Is it because,
Sorry, I never said it was a group homomorphism.
but here you get some graded. This is basically Picard. So it means that it has some homomorphism into graded.
Right. There's a homomorphism into GUR1, but it's like, OK, I would have to think about this, but I think it's roughly like you send a line bundle to 1 minus a line bundle.
So you have like, if you write multiplication in terms of 1 plus x, then the operation is like x plus y plus xy, and the xy is thrown away when you take associated grade.
Right.
That's what happens.
Right. I think that's right. Yeah. Thank you. Yeah. So what they proved is that Italki theory is the same as topological cyclic homology of R. Now, you don't really need, again, everything is p-adically completed. So there's this entire industry of people that compute K theory using methods related to topological cyclic homology. So there's topological Hodge homology that you define first, and then you put more and more structure on it until you get to topological cyclic homology. And that's somehow the best approximation to K theory that comes out of thinking about Hodge homology over the sphere spectrum. And what the theorem is saying is that in this p-adic setting, the two are actually the same. So it's an excellent approximation. You can just use TC. And so the way this theorem is proven is once you just plug in Clausen, Matthew, Morrow, and you're allowed to replace K tau with topological cyclic homology. And as I tried to hint, TC is built out from all of these other invariants. And what you do is you prove an analogous theorem for each of those invariants and check that it survives the process of building the fancier ones out of the less fancy ones. And so what we do in that paper is a variant of theorem. Let me call this theorem A, just so that if I want to refer to it later, I can call it A. So there's a variant of theorem A for all the attached invariants. So topological Hodge homology, something called I don't know if this TC minus of R, topological periodic homology of R, and TC of R. And in all cases, the associated graded is related to prismatic homology, and it's going to be related to the intermediate things that showed up in building syntomic homology from prismatic homology. So with GUR I, given by, let's see, so for THH, you get the associated graded of the Nygot filtration. Okay, I'll probably get my shifts wrong, so I apologize for that. For TC minus, you just get the layers of the filtration. For TP, you just get a two-periodic version of prismatic homology itself. And then for TC, you get asymptotic homology. And the way in which ZP of I was built up from prismatic homology mirrors the way in which TC is built up from the rest of the pieces over here. So there's, OK, yeah. sorry, are there any questions about this more slightly vague statement?
There will be a result in algebra which follows from this.
Yeah, so I'm about to give you two applications of this. One is an application in topology, and one is an application in algebra. Yeah. Right, so. So the question was, can you do something about Chow groups from this process? I mean, in some sense, the example I'm going to give with PIC is an example of that, because PIC is the easiest example of a Chow group. But I don't know any other examples. I mean, this étale descent procedure really seems hard to control once you go beyond codimension 1. Okay, so some applications. So maybe let me first mention the application to topology. And so, I mean, Bott periodicity said that if you think about the K-theory of a space, but you just look at it locally on the space, then it only lives in even degrees. Because locally it's just the K-theory of a point, and a point only has K-theory in even degrees. And so the odd degree cohomology groups vanish locally. And so there's an analog of that in algebra. This is the odd vanishing theorem. So this came out of computing Syntomic homology using other techniques in prismatic homology and plugging that into this theorem over here. And here's the output. So the odd K-theory vanishes in a certain sense. So this is, okay, so this is syntomic locally. So the notion of locality is going to be the syntomic one. And on syntomic rings. Okay, so the word syntomic is showing up in a lot of different places. I apologize for that. Basically, syntomic means that it's a local complete intersection. So it looks like you have a bunch of variables, and then you mod out by a regular sequence. So equations that are sort of as transverse as they could be. So that's the class of rings for which this machinery works the best. It includes things like smooth algebras over a field. And syntomic locally means you allow certain covers, which are themselves syntomic morphisms. So a typical example would be you allow yourself to extract a p-th root of a variable. That would be an example of a syntomic cover. And so this is in some sense the best you can do, because I mean, you might wonder if Zariski or étale locally, the étale K-theory vanishes. But it turns out that that's just not true. I mean, the Zariski or the étale topology is too coarse to kill K-theory classes. And so you have to go up to something slightly big, and syntomic one does the job. Yeah. And so the proof of this is actually slightly funny. I'm not going to explain it. But sort of the key ingredient of the proof comes from commutative algebra. So I mentioned yesterday in my talk that there was this problem called the direct summand conjecture in commutative algebra that was solved by Yves André 3 or 4 years ago. In the process of solving this problem, he proved a certain lemma about perfectoid rings. And that lemma is what makes this proof tick. So if you like, it's some application of algebra to topology. And more generally, you can use, I mean, you can see where I'm going with this. You can use this theorem to actually compute examples of K-theory once you know how to compute things on the syntomic side. And so this was done at least in a few cases by various people. So get new calculations of K-theory.
So when you say K, do you feel it's neutral K or
Since I'm working locally, syntomic locally, it doesn't matter, because étale covers the syntomic covers. Sorry, the question was whether I put K or K étale over here, and the answer was it doesn't matter. So you get new calculations of actual K-theory. I'll just mention one example. So this was worked out by Akhil, Matthew, and then also Yuri Salima. And what they computed was, well, I think, okay, so I think they give a new proof of an older calculation by, I forgot to write down the names, Hesselholt and I think Madsen, but someone from the audience can correct me if I'm wrong. So the K-theory of truncated polynomial rings over a field of characteristic P was computed exactly in the past. And Matthew and Salima give a new proof of it, which is somewhat more efficient using this theorem. And their method also gives you something more. So it identifies what the structure looks like multiplicatively. Previously, I think it was only done additively. And I'll mention one more application at the end of the talk. And so the other application I wanted to mention right now is in the other direction. So this was going from these kind of tools in commutative algebra to some vanishing results in K-theory. You can also use this fiber sequence, as I said, sort of computing Picard groups in terms of prismatic homology to get results in algebra. And so here's purity theorems. And so these were, there were a bunch of results that were conjectured by Gaber and then proven recently using these ideas by Chisnavikus and Scholze. And the statements are, they concern what happens to Picard groups or Brouwer groups when you remove small codimension subsets. So that if everything was as nice as possible and things were like manifolds, you would expect that low degree cohomology should not be affected if you remove something of very high codimension. And this is a version of that result in algebra. And so here's the statement. So R comma M is a Noetherian local LCI ring. It's a local complete intersection. And then what they prove is that, first of all, if you look at the Picard group of spec R minus the point, so you're removing something of very high codimension, the codimension being the dimension of the ring, and you look at the torsion in here, this is 0 for if the dimension of R is at least 3. And there's a similar result for Brouwer groups if you go 1 degree higher everywhere. So the Brouwer group of R is the same as the Brouwer group of the same punctured guy. So the Brouwer group is insensitive to removing small codimension subsets if small means at least 4 now. So. And so again, if you're in some classical setting, like if R is the local ring of a variety over the complex numbers, these results were known by comparing it to usual singular cohomology and then using purity theorems for singular cohomology. But in this kind of generality, where R could be, something over the p-adic integers, we don't have any topological tools to play with. And the way they prove this theorem is exactly what I was alluding to before. You think of these guys as being some cohomology groups of this guy is the same as this guy, and this guy is computed in terms of prismatic cohomology, which is much more directly connected to algebra. So you can do like commutative algebra arguments like depth and so on.
So in equal characteristics, this was known before?
So I think actually an equal characteristic, this is also new in the sort of sharpest possible dimension. If the dimensions were upped by 1, I believe it was known in equal characteristic. But this kind of off by 1 problem often came up in previous arguments. And the way this new argument gets around it is, again, I'm not going to be able to make this precise, but prismatic homology somehow has dimension 1 more than the dimension of the ring. And then this extra dimension often solves these off by 1 problems that come up.
But these are sharp bounds.
These are sharp bounds, yeah. Okay, so think I'm doing OK.
And the other versions of this with hierarchical homology?
The question was, are there versions of this with hierarchical homology? Yeah, so there are, but those are known before. So somehow what happens is everything was known for prime to p, for the prime to p aspect of it. So I'm working in the with p-adically complete rings. And if I only care about, for example, the prime to p torsion, this was already known. So all the information is local at p. And what happens is that this invariant, when you p-adically complete it, only has pick and brar. There's nothing beyond it. So there's a vanishing theorem. I think that's due to trigger. Well, I mean, you can also prove it using this formula for ZP of 1. Other questions? It doesn't have to be, but as I said, since the theorem was already known in every other case, you can reduce to the case where R is p-adically complete by some formal gluing argument.
And does it imply also a statement about removing not a point, but sub-variety?
Yeah. So there's some so sorry, the question was, is there a more general version of this where you don't remove a point? And the answer is yeah, there's some general yoga where if you prove statements like this for local rings, then you get analogous statements for where you have some x and then you remove some z, where the codimension of z at every point is at least 3 or 4. Other questions? OK, so what I want to do now is give you a very brief idea of how, I guess it's gone. Sorry. Of how the filtration is constructed. Not to give you any details, but just to give you a flavor of the kind of tools that are used. And then at the end of the talk, I'll try to explain some very recent work by some people in the audience that gives a better way of doing it. So, idea of the construction of this filtration. Like, where does the filtration actually come from? And so I'll just do it in a toy example. Or, I mean, it's not that toy, but. So say R is syntomic over the p-adic integers. And again, if you don't like this generality, just think about the case of a polynomial ring in one variable over a finite field. We want to construct this filtration on the topological cyclic homology of R, or any of these other variants that showed up along the way. And the way to do that is to try and resolve your ring itself. So we're going to pick highly ramified covers of the ring and then try to compute these invariants for these highly ramified covers and then try to descend the information back down. And this idea of like adding ramification, simplifying things shows up a lot in this entire subject. So I'm going to choose R to S, which is an ind syntomic cover. Again, I'll give an example, such that this ring S is supposed to be highly ramified. And one way to say it is that S upon P has a surjective Frobenius. So it's really huge. Again, in this example, you could take FP adjoin not just X, but all the P power roots of X. So some non-Noetherian ring. So you've thrown in all this ramification. And why does it turn out to be useful? It's useful because these invariants take on a really simple shape for such rings. And so I'm going to, first of all, give a name to the resolution I get of R using S. And so S dot is going to be the name for this diagram. So I just take iterated tensor products of R over S. It's the check nerve of this map. And it's sort of a standard recipe for resolving R using S. It's the resolution in the sense that if you convert this into a complex and compute its cohomology, you get R in degree 0 and nothing in higher degrees. So it's a resolution. And then the definition of the motivic filtration, say for THH, is the following. So I'm trying to define THH with its motivic filtration. And this is going to be the inverse limit over this diagram of THH of the terms of the diagram endowed with their motivic filtration. So I've just pushed the problem to defining the motivic filtration for these S's, S0, S1, and so on. But there it turns out to be very simple. So it's the double speed Postnikov filtration. So just the canonical filtration of any complex done at twice the speed. And so it turns out that part of the, I mean, there's lots of things that make this work, but part of it is that for these rings that show up in this diagram, all these invariants only have homotopy in even degrees. There's no odd cohomology or autohomotopy. And you can, the exact same definition applies to every other version of T in this story. So let me just maybe make one comment on what is actually powering this. So why can you do this? Well, the first thing that better be true if you do this is that if you forget the filtrations, then you haven't changed what you're trying to compute. You want this limit of these guys to be THH of R. And so that's true. And so you have to prove that. And so the statement is that THH is a sheaf for this topology. What did I use in Syntomic? Okay, and then there's a standard kind of yoga for proving this by reducing down to the case of the cotangent complex, which was known 10 years ago. And then the second thing is, so this will tell you that at least this is a sensible definition in that you're computing a filtration on THH of R. And so the second thing you need is some ability to compute what these terms look like. And that's provided by fundamental calculation of Buckstead. And so Buckstead computed what happens when S is just the finite field itself, and you get a really nice answer. So pi star of THH of Fp is Fp adjoin U, where U has degree 2. So it's a polynomial ring on a class in pi 2. And this is really a calculational theorem. I would really like some more conceptual way of saying this, like some kind of 1 or 2 line proof saying Fp has blah, 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 and therefore THH looks like this. But I don't know any proof of this theorem that avoids calculations, and it's extremely surprising. Because if you didn't do topological Hodge homology, if you did usual Hodge homology over the integers, so you stay in algebra, then you would get a divided power algebra over here. And so somehow passing from the integers to the sphere spectrum converts a divided power algebra into this really nice polynomial algebra. And that's very important for that calculation. Okay. Right. So I've told you about what this motivic filtration is. I gave you some construction of it, and I told you at least 2 ways you might use it in either topology or in algebra. And so what I want to do in my last 10 minutes is just tell you a little bit about some very recent developments in the subject, so from the last few months. The first of these I already mentioned in my first talk, but I'll mention it again. So it's a new calculation. It's a calculation of the K-theory of things like Z mod p squared. So Anteo, Krause, Nicholas. And so I mentioned on the first day that they proved this even vanishing theorem. So they proved that the K-theory of Z mod p squared, for example, vanishes in sufficiently large even degrees. But they do something much more. What they really do is that they give an algorithm to compute the Syntomic homology of rings like Z mod p to the n. And then you run the algorithm to get the vanishing theorem. So more precisely, given any finite extension of a p-adic field, you get an algorithm to calculate these syntomic complexes, Zp of I, of truncations of OK by powers of its uniformizer. So it's a powers of uniformizer. And then by theorem A, this gives you an algorithm to calculate K-theory. It doesn't matter. It's the usual one. So one thing I should have pointed out explicitly is usually the process of Italki is really drastic. It changes a lot of things. As I said earlier, there's one situation in which that doesn't happen, which is usually regarded as a pathology. So if you're working in characteristic P and you do a Italki homology of varieties with mod P coefficients, it's considered pathological or stupid because it's not the right size because somehow there are too few Ital covers. So, but the fact that there are too few Ital covers means Italki is also not that drastic. And so this Italki process for p-adically complete invariants is pretty tame. And so they actually compute it for OK mod pi to the n. Yeah, so it's a good question. I'm not exactly sure. So I think this is related to, sorry, the question was the connection between the odd and even vanishing theorem. I think the fact that the odd vanishing theorem is true tells you that the bounds that show up in the even vanishing theorem will have to depend on the parameters in the situation. So the local field K and the power of n you're looking at. Beyond that, I'm not exactly sure how to relate one to the other. Yeah.
Also, I have a question about this statement. So suppose R is not a complete intersection, but maybe, let's say, integral domain, but not complete intersection. Is this false?
So the question was, what happens if you drop the LCI assumption but keep it like a domain? Yeah, I think you more or less need the LCI assumption for this. I believe it's false if you don't assume it's LCI. Even Cohen-Macaulay is not enough. I don't know an example off the top of my head, but I'm fairly sure that LCI is more or less the optimal hypothesis here. Because, well, sorry, if you tried to prove this analogous, you can ask your question over the complex numbers. What are the assumptions you need for a purity theorem in Picard and Brar for varieties over the complex numbers? And the argument I know relies on the fact that the constant sheaf is perverse. And so I don't know something weaker than LCI where this happens that often. Yeah. Great. So the other, well, OK, I want to mention, I wanted to give some idea of, like, they make a really nice observation in this paper, and let me just mention it. So, because it's easy. And the observation is just some property of prismatic homology that wasn't noticed before. And so this observation is only going to make sense if you know a little bit about the subject. So please ignore it otherwise. But let me say it. So given a prism A comma I, and an A mod I algebra R, the observation is that the complex computing relative prismatic homology, prism R over A, does not depend on I. And so there could be multiple prism structures on A for which R is an A mod I algebra. There could be I1 and I2, and R could be an algebra over both I1 and I2. And the observation is that it doesn't matter which one you use. And this makes certain independence of choices type arguments much easier. OK. And the second thing I wanted to mention is this work I alluded to earlier. So it's by Jeremy Hahn, Harpon, Ruskin, and Dylan Wilson. And what they observe is this way of constructing the motivic filtration on THH of R actually doesn't really have anything to do with commutative algebra or rings. It's something that you can make sense of directly in terms of just the E infinity ring THH of R itself and not what its definition is. And so more precisely, they give a, let me say it this way. So purely homotopical construction of the motivic filtration. And I will say what this looks like in this example, just to compare it with what happened before. So if R is syntomic over ZP as before, I gave you a definition over there, and their definition would be the following. So THH of R, comma, the motivic filtration is an inverse limit again, but over something which doesn't care what the specific decorations here are. So THH of R to A, where this is a even E infinity ring, meaning its homotopy is in even degrees, and this is a map of E infinity rings. And then over this the category of all such things, okay, modulo set theory issues, you can just look at A and endow it again with the double speed Postnikov filtration. And then, if I'm not butchering the theorem, I believe this is what it says in this case. And so you see the way, if you write it like this, you can just treat THH of R as a black box. It's an E infinity ring that you plug in, and you get as an output some filtration on it. In particular, you can use their theory to make sense of the motivic filtration on THH of an E infinity ring, not just THH of a usual ring. And so I think this is an interesting direction for the future. Okay, I was probably going to say one more thing, but it's 5:29 and it's Friday. So it's also not that interesting. So let me just stop here. Thank you.
Any questions?
Does it left without also for other theorems?
Yes, yes. I think the same formula applies for all the T invariants. I mean, okay, again, my understanding is that the way you prove this theorem is by observing that this limit can be computed as this limit. So this is like a subdiagram for all such A's, and by some descent argument, the limits will be the same.
But is the K-theory for the p-adic integer known?
Yeah, so Hesselt and Madsen computed K-theory of OK for any finite extension K of QP. And I mean, there's this Quillen-Lichtenbaum phenomenon there. So it's basically this, understanding it is essentially the same as understanding the Galois homology of the fraction field with coefficients in ZP of I, in the usual p-adic Tate twist. Except for like weight 0 and 1, you have to do something.
Yeah, the question? So it's a convention on that, but you mentioned some in the middle of the talk that symptomic calculations often help to fix this issue of being off by 1.
Uh-huh.
Can this be put in the kind of perversities? Because that's
Wait, sorry, I didn't follow that. I didn't follow that question.
Can it be can be rephrased in terms of certain T structures on the derived case?
I haven't thought about it that way. But I mean, it's, oh, sorry, thank you. So the question was, there's this phenomenon that I alluded to about off by 1 problems in cohomological indices being fixed by working with prismatic homology rather than the usual coherent story, or syntomic homology. And the question was, can this be put in some more general framework involving T structures? And I don't know the answer. But I mean, roughly, what saves the day is that these invariants are p-torsion free. And so somehow you, even the old invariant you would care about, like if you care about p torsion in the Picard group, for example, you're doing cohomology with mu p coefficients. Mu p is like zp of 1 reduced mod p. And so what you're observing is that this invariant is the mod p reduction of something else, and using that something else to get some additional structure in this guy. And so, I mean, yeah, it seems like there should be some algebraic way of capturing this, but I don't know, something simple to say.